Hi, let's talk about sequences. There are a few things you have to understand about sequences before you move on to series, where the bulk of the topics are. You have to understand what a sequence is, how to find the formula for the nth term of a sequence. You have to be able to find the limit of an infinite sequence and talk about the convergence and divergence. So first of all, what is a sequence really? It's just a list of numbers. We can use brace brackets and commas to separate them. We often use the variable a to represent a term in the sequence, and we name the term by its rank, a1, a2, a3, and so on. So when we talk about the nth term of a sequence, n is the rank of that term. Another notation for expressing sequences is using the formula inside the curly brackets. And optionally, you can indicate what the rank of the first term is. In this case, you want to plug in the value 3 to figure out what the first term is. So the first term would be 6 plus 5, 11. And it's always going to increase by 1 when you go to the next term. So if you want the second term, plug in n equals 4. You could also give the formula for the nth term of a sequence. A recursive sequence always depends on at least one of the values that came before. So you have to calculate all the values that came before. For instance, if you want to figure out what the 10th term in a particular sequence is, you've got to calculate the first 9 first. The Fibonacci sequence is an example of a famous sequence of numbers. The first two terms are both 1. To figure out the nth term, you always add up the two terms that came just before. So the first two terms are each 1. The third term is going to be 1 plus 1, which is 2. The fourth term is going to be 1 plus 2. The fifth term is going to be 2 plus 3, and so on and so on. One of the things you might have to do is figure out what the formula for the nth term of a sequence is. So this is all about finding patterns. In this list of numbers, you can see that to go from one term to the next, you have to add 3. It's a lot like a linear function. So you can think of this as a being a function of n, the rank, just like y is a function of x when we graph linear functions. So if all of the a values are increasing by 3, it's as if it has a slope of 3. So that's what's going to multiply n. And then you just have to figure out what the last value is. What is it that you have to add or subtract to make this formula work? You can do that by just plugging in a value of n. If we look at the first term, n is 1. 3 times 1 is 3. What do I have to add or subtract to get to my term value of negative 6? I have to subtract 9. So 3n minus 9 works. And you can test it for all of the values. The next sequence example here you should recognize is a list of perfect squares. The first term is 1 squared, the second term is 2 squared, third term is 3 squared. So how do we write the formula? It's simply n squared. This is an example that builds upon the one before. The difference here is that you can see the terms are alternating signs. So this is called an alternating sequence. How do we express every second value as a negative number? We can take negative 1 and raise it to the power of the term value. If n is 1, for instance, we say negative 1 to the power of 1, which is a negative number. If n is 2, negative 1 squared is a positive number. It bounces back and forth. It depends if n is even or if n is odd. But what if the first term was positive and the second term was negative? Then we could raise negative 1 to the power of n plus 1. So if n is 1, the exponents are actually going to be an even value. So the first term will end up being a positive number. You could have said n minus 1 instead of n plus 1. it would give you the same result. In this sequence of numbers, to get from one term to the next, we multiply by 3. So that's very much like an exponential function, where the base of the power is 3. In this example, we started with the value 2, so that's like our initial value in the exponential function. In this example, there are a few different things going on. First of all, it's alternating, so we can use the same trick of putting -1 to the power of n, or n minus 1, or n plus 1 in the front. And then we also have a fraction, and there's no pattern in the numerator, it's always 5. But in the denominator, we can see that there's a pattern of always adding 2. So it's as if the denominator only is a linear function, like in the first example. -1 to the n minus 1 takes care of the alternating part. 5 is always in the numerator. The denominator is simply 2n. That works. When n is 1, our value is 2. When n is 2, our value is 4. We don't have to add or subtract anything to get to the right number. Now this sequence is a bit tricky. The values are bouncing back and forth between a minimum and a maximum value, which reminds me of a periodic function. When you're faced with a periodic function, think about what the middle value is, the one that's between the minimum and the maximum. To do that, just find the average. So the average of 2 and 10 is 6. 6 minus 4 is 2. 6 plus 4 is 10. So we can take the 4 and multiply it by either 1 or -1, and then add it to 6. Another way we can express this one is with a cosine function. We know that multiples of pi, when we take the cosine, would give us 1 or -1. In other words, cos of 0 is 1, whereas cos of pi is -1. Cos of 2 pi is +1 again. And it goes back and forth and back and forth. We want to add or subtract 4 from 6. Another important concept with sequences is looking at the end behavior of the sequence. So as n approaches infinity, what is the last term? Or is there a last term? In other words, is there a limit? Let's look at this example. We can see that as n increases, the values, the terms, are getting smaller. So 3/2, 3/3, 3/4, 3/5. The numbers are getting smaller and smaller. It's like looking at a function. The dependent variable is the term value, and the independent variable is n, or the rank. So as n increases, the term decreases. This looks like an inverse function that has a horizontal asymptote at y equals 0, or an equals 0. So we can say that the limit of this sequence as n approaches infinity is 0. If we wanted to figure it out, without actually graphing it, of course we can just take the limit of the algebraic expression. So what is the limit as n approaches infinity of 3/n? We didn't have to graph it to see that it's equal to 0. As n approaches infinity, a number over infinity becomes 0. Basic limit rules. Speaking of, you'll be finding lots of limits when you're dealing with sequences and upcoming series. So review your limit tricks. L'Hopital's rule, the squeeze theorem. You may have to use any and all of these. An important theorem when we're talking about sequences is that if the limit of the absolute value of our term is 0, then that means that the nth term of the sequence is 0. In other words, we can ignore the -1 if there is one. or the fact that it's an alternating sequence. We'll see that in a minute. When we talk about the limits of sequences, this brings us to the convergence and the divergence of the sequence. If the sequence does have a limit, as n becomes infinitely large, then we say it converges. If it has no limit, or if the number approaches infinity, then we say that it diverges. It's just like improper integrals. For example, is this sequence convergent or divergent? This is an alternating sequence, but we just saw that if we take the limit of the absolute value as n goes to infinity and it's equal to 0, then we can conclude that the nth term is also 0. So all we have to do is take off the negative 1 to the n minus 1, because the absolute value means take the positive. And we'll take the limit of 5 over 2n instead. And this is 0. A number over infinity is 0. This means that the nth term of the sequence is 0, because its absolute value was. Therefore, we can conclude that the sequence converges, since the limit exists. Here's another example. We need to take the limit as n goes to infinity to see if this is convergent or divergent. So we're looking at a classic limit question now. If we plugged in infinity, we would get ln of infinity divided by infinity, which is infinity over infinity, and that is an indeterminate form. So we'll use L'Hopital's rule, where we take the derivative of the top and the derivative of the bottom, and now we can see that the top goes to 0, and 0 over 1 is 0. So the limit exists and the sequence converges. Here's an example that involves factorials. Do we remember what a factorial is? 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. You just take the value in front of the exclamation mark and multiply it by the number 1 less than that over and over. So if this was 3 factorial, it would be 3 times 2 times 1. Just multiply the number by 1 less than until you get down to 1. Let's see if we can clean up this expression a little bit, because we can't easily take limits involving factorials. If we expand the top, it would be n plus 1 times n minus 1, and you just keep subtracting 1 until you get down to 1. Look at the bottom. It's n times n minus 1 times n minus 2, and so on and so on and so on, down to 1. Now a lot of this stuff is going to cancel out. So really what you're left with is n plus 1. So an is exactly the same as n plus 1. What's the limit as n approaches infinity? It's infinity. So the sequence diverges. What about cos of n pi? We just saw this in an earlier question. When n is 1, the term is cos of pi, which is negative 1. When n is 2, the value is cos of 2 pi, which is 1. When n is 3, the term is cos of 3 pi, which is negative 1. It keeps bouncing back and forth between positive 1 and negative 1. In this case, the limit doesn't exist, and so the sequence also diverges. What about cos of pi over n instead of pi times n? Let's look at just the limit of the inside. The limit as n approaches infinity of pi over n is 0. And we can use one of the limit rules. Since the cosine of the function is continuous at 0, then we can say that cosine of the limit is the same thing as the limit of the cosine. Therefore, cosine of 0 is equal to 1, and the sequence converges.